Welcome, everyone. I'm going to give everyone a second to get settled in here before we get started. Thank you all so much for joining us. Alrighty, welcome everyone. You are joining us for Manufacturing Solutions for Hollow Core Fibers, presented by Nextrom and hosted by Photonics Media. Today's speaker is Joni Aaltonen, Product Manager for Specialty Fiber at Nextrom. Joni joins us with 13 years of engineering experience, including 8 in fiber optics, along with a bachelor's degree in mechanical engineering. He has designed and installed fiber manufacturing equipment across 3 continents, giving him a strong balance of innovation and practical expertise. A quick note to our viewers, feel free to ask questions in the chat box at any time. If you experience any technical issues during the event, please try logging out and back in to rejoin the session. Also, registrants will receive a link to this webinar recording in your inbox after the session. That's all from me. Joni, we appreciate you for taking the time, to join us today.
Thank you, Jacob, and hello everyone. Good morning, good afternoon, good evening. I'm happy to be here today. As mentioned, I'm Joni Aaltonen, Product Manager for Specialty Fiber here in Nextrom, and today I'm here to talk a few words about manufacturing solutions for hollow core fibers. So I hope you enjoy and hope we all learn something today to take home with us. So my agenda today will roughly be, I'll quickly introduce, if you're not familiar, what is hollow core fiber and why it is. I'm going to be mostly focusing on the manufacturing challenges and giving some hints how Nextrom can help with those, and I'm going to quickly summarize this. I will be using approximately 30 minutes of your time. I want to value your precious time, so without further ado, let's go. So starting with the hollow core fiber, what it is and why. So as the name states, it's hollow core. So there is no solid core. It is an optical fiber, but the inside is hollow, and light that's transmitted through the optic fiber goes through air or vacuum, or potentially some other gas. But the main point is that there is no glass media where the light is traveling. There are several different types of hollow core fibers: photonic band gaps, revolver fibers, anti-resonant fibers, really wide variety of different types of fibers, and I'm not going to be focusing on any specific one in this webinar, but just to give a general idea that there are many different types for many different applications. Then briefly about why you should be interested in hollow core fiber. Why it's a thing? So hollow core fiber provides a lot of benefits comparing to traditional optical fibers, and I am mostly referring to telecom fibers when I mention traditional optical fibers. Maybe the biggest thing is lower latency. So hollow core fibers carry up to 33% reduction compared to solid core fibers. So this latency, for example, allows longer distances without losing the signal. So talking about, for example, data centers, you can locate your endpoints and terminals further away without any additional loss of signals. This gives you some freedoms in your area of industry. There is less attenuation. So there have been reports of even below 0.1 decibels per kilometer. So this is comparing to telecom fibers significant. There is a reduction in nonlinear effects. This allows much higher power and distance for transmission. Hollow core fibers also have higher damage threshold and power handling. This is especially good for high power lasers, so those benefit from hollow core fibers. And the hollow core fiber, it has a larger transmission band. So comparing to those traditional optical fibers, these are just to name a few. There are several other benefits also: radiation resistance, chromatic dispersions, etc. But a really valuable option for whatever your specific need might be. Then to mention a couple use cases where hollow core fibers are emerging. Maybe the biggest thing at the moment is data center connectivity, both intra data center, inter data center, and tower to data center. So intra data center is within the center. Inter means, of course, that between two centers. And given the benefits from the previous slides, this allows longer distances, which is giving much more flexibility in locating your terminals. And also tower to DC, a lot of traffic is mobile, of course, but that traffic goes through a tower. So improving that signal and that traffic between the cell tower and the data center, hollow core fibers are really good in that. There are also a lot of medical applications, and I'm sure there's a lot more to come. As I mentioned, the power handling capabilities for laser applications. And there's sensing technology benefits also, for example, different gyroscopes, or if you fill a hollow core fiber with different gases for specific purposes, you get a whole new variety of different possibilities with the hollow core fibers. But then getting to my main agenda today is the manufacturing challenges. So if hollow core fiber has so many benefits over other fibers, why isn't all fibers like that? To put it in brief, it's very difficult to manufacture it. So telecom fibers have been around for decades now, and that has been perfected quite well. But the hollow core fiber portion brings a lot new challenges to the table. So I will be talking briefly about the preforms, what cleanliness and accuracy means in there. I'm going to be talking about the draw, so about the furnace, its temperature and uniformity of that temperature, what's the hollow core fiber has to do with draw tension and controlling pressure inside preform. I'm going to touch briefly on this. And also to get a valid fiber out of the process, a proof testing is required. And there are a couple of things, for example, lower widening tension and the fiber line accuracy, which are few of the key elements in drawing A-class fiber. So when it comes to preforms, the process cleanliness is critical. So any internal geometry in your preform, doesn't matter how you manufacture it, if it's extruded, if it's drilled, if it's welded, if it's anything, the internal geometries are susceptible to particles. So in case of a particle inside the preform, you might be seeing inconsistencies in the preform, and that might cause you either loss in performance or fiber break. And preparing any raw materials with acid washer, it only ensures clean basis for manufacturing a preform. So let's say you stack a preform, you have your raw materials, but while you're doing the process steps, there is a chance that you're introducing particles or contaminants into the preform. So why Nextrom is a good choice for manufacturing those? So first of all, we have a glassworking lathe where we have tapped into our decades of MCVD technology know-how. So what we've introduced is an fluorine source for processing different tubes and preforms in a glassworking lathe. So with the fluorine, you can etch and clean those tubes and finish preforms. So doesn't matter what manufacturing method you use for making the preforms, you can do the final fluorine pass and clean out the contaminants from inside to ensure that your process stays stable and as good up to standards as possible throughout the rest of the handling of the glass. What our glassworking lathe also has is a hood around it, so it is not an open one. So, and there is a option for clean air supply, so a HEPA filtered air blower is provided for the process also. This increases the process cleanliness and reduces any chances of contaminants from the environment. What we also offer, and I'm touching a little bit into the draw side already, is a rod or capillary draw line. So you can have a capillary draw line. So in case you're using capillaries for your preform manufacturing, This allows you to control your capillary supply. You have much more freedom and flexibility over any other supplier. So, and if you want to trial different sizes, or you have a specific size or need, you can control that supply on your own. Also, this allows to adjust the cross-sectional area and the wall thickness of your capillaries. So a lot of freedom over the process in there. What we also have in the capillary draw line is online tension measurement option. So we use a Caterpillar capstan for drawing those capillaries and rods, but the capstan has a tension measurement. So this gives you an additional data point for the feedback loop of the whole draw. So this gives you much more control for more precise diameters and more precise dimensions. And what's our benefit also is that we do have a dual-sided draw towers for using one side for fiber draw and the other side for capillaries and rods to draw. This saves a bit on the footprint and some infrastructure costs, of course, when you have everything centralized. Then I'd like to talk a bit about the draw itself. So now that we've come up with a preform, which is clean, perfect, ready to be drawn, we need to start the draw itself. There's a few key points related to the furnace, related to pressure control, the drawing tension, and then winding the fiber itself. So starting off with the furnace, the temperature stability is paramount. So hollow core fibers and the preforms tend to have complex structures inside because the preform is hollow itself also. So where the fiber comes from, it's hollow, and maintaining a stable and uniform temperature in there is really important. So this means that you need to be able to melt the whole preform throughout and uniformly. So it doesn't matter what type of preform you have, what kind of design you have, you want to have uniform temperature. Then initiating the draw, I'm calling it the drop. Some of you might be familiar with the term, but the challenge is in initiating the draw of these structured fibers. So when you start the draw, there will be the drop. And with microstructured fibers or structured fibers, this drop tends to be larger in diameter than, for example, in telecom preforms. And there might be some issues that the drop doesn't clear the furnace exit because you want to keep the furnace as closed as possible, but then you want to open it as much as needed for the big drop. So there are a couple of challenges. And also the gas flows inside the furnace because we keep it in inert condition. Those flows need to be optimized to support these stable conditions. So what we've done is used our experience through over 50 delivered furnaces to optimize those glass flows and temperature distributions. We do use resistive furnaces, which means that there is a graphite element inside, and that geometry we have been optimizing for over 50 furnaces. Then the exit of the furnace has been modified for such microstructured fiber. I must at this point mention that this can be retrofitted to practically any of those over 50 furnaces. Then we have introduced internal pressure measurement. So we have one additional data point on the gas flows and the gas behavior inside the furnace. So we have a pressure measurement available for the exit of the furnace. So this gives a bit more data and a bit more control over the conditions inside the furnace. And the furnace design allows us to get a diameter variation as low as plus minus 0.1 micrometers. Then about the pressure control. So the preform is hollow. It does have some sections, some elements, depending on the fiber design. But anyways, there are hollow sections inside the preform. And when we are melting that preform, or getting it to a nearly molten state, there is a risk that we can't maintain the geometry. So there are different different features inside the preform, and we want to keep those dimensions, distances, thicknesses, etc., as stable as possible. So we need to introduce some external forces, in this case with pressure of an inert gas. And the scales that we're talking about are so small. These different elements and geometries inside the preform can be, it's in a micrometer range anyways, especially in the final product. So this pressure control needs to be extremely capable, up down to a microbar range for both adjustments and stability. So it's really critical that you're able to modify the or control the geometries. What we can offer is a pressure controller, and we can integrate that into our line control. So we do have available a pressure controller that can perform at such a low range. I do need to mention that any kind of plugs and connectivity to the preform, since there are several different preform and fiber designs, it is very difficult to come up with a universal solution. So this is still left to the customer. We are, of course, very happy to work with everybody, but this is something that, to be honest, we don't yet have in our portfolio. But the pressure control is there. We just need to figure out how to connect to your preform. Then about the drawing tension. So these microstructured fibers, hollow core fibers, they demand higher tension, and this is due to the lower temperature that the fibers are drawn. And the fibers are drawn in lower temperature because if you keep the temperature up, you risk that you're starting to melt a certain side of the preform faster, or some parts don't melt or they start to sag. So you need to keep the temperature a little bit lower, but the trade-off is that the tension is much higher. So for this reason, we have increased our pulling tension capability in our capstan. And we, of course, have a sophisticated control loop across the whole line equipment. And this kind of goes back to the feeding of the preform, the pressure control, and the whole line works in unison throughout. Now that we have melted the fiber, we need to catch it somewhere. So we have melted it, we've drawn it, and we need to wind the fiber somewhere. So what we would like to offer in this case is a dual take-up for a couple of reasons. There's few benefits. First of all, with the dual take-up, you do have the sampling capability. So this means that when you're starting your process, you're taking the first steps into drawing the hollow core fiber. You want to make sure that all the process parameters, all the features in the fiber are dialed in. So actual manual sampling capability gives you the possibility that you draw a bit to the first spool, then you change it to the second spool, so you don't interrupt the draw. It's continuous draw. And while you're drawing to the second spool, you take your measurements from the first one, put it under a microscope and measure it, whatever is the desired requirement that you're looking for it. You can tune your process, and this helps speed up the process tuning. And as the changeover is automatic, you don't need to interrupt your draw process at all. And the catcher also has been customized a little bit for these purposes. So hollow core fiber has a couple of peculiarities when it comes to catching it, but these are really similar to other fibers. But there's a couple of herbs and spices in that recipe. And also sampling capability. This is the initial steps in the process, but once you figured your process parameters, then you want to speed up, and we can support these up to over 1,000 meters per minute. So these machines are capable for that. So your productivity ceiling is not this will not be a bottleneck in that case. But now the fiber has been drawn to a spool. It's practically ready, but we still need to do some quality control. So proof testing the hollow core fiber. The custom winding tension is a tricky part because the cross-sectional areas differ from different fiber types. This means that your winding tension needs to be able to adapt that. So winding tension might be lower, might be higher, might be anyways custom. So this is a tricky part. And when the tension changes, the alignment plays a much bigger role. So the custom tension, the fiber can be very susceptible to any spin. So this means that the wheel design and the wheel alignment needs to be really accurate. And also the machine has to be extremely rigid and it must not introduce any vibration or alignment drift to the whole process, meaning that you have your wheels dialed in, those need to stay in there and those need to be perfectly aligned. What we have done in the picture you see our OFC 35SF, that's our specialty proof testing machine. And we paid a lot of attention to the mechanicals of this proof tester to accommodate these higher accuracy requirements of the hollow core fibers. That was the part of the manufacturing itself. I like to keep it brief. I like to value your time. But the further considerations, what we have identified is the industry standardization. So my mind likes to compare everything into the telecom fibers, and the telecom fiber industry is very standardized and it's really been there for decades. So it's natural that everything comes into a one uniform, under one umbrella of standards. But with the hollow core fibers, the industry has not yet been standardized as much. And there are, of course, because there are several different fiber designs for different applications, it could be that there will not be one single standard for everything, but meaning that this is still a bit of everybody's game at this moment. Also, the splicing and connectivity. What has been learned in the telecom side doesn't directly apply into hollow core fiber realm. As the fiber standards in the ecosystem are not fully developed yet, it might be that manufacturers need to design and come up with their own connectivity solutions. But starting to sum this up, generally hollow core fiber, it provides great benefits over telecom or traditional other fibers, and the forecasts are that the demand will grow. Here you see Ericsson's forecast up to year 2031. So we are in 2025, and their forecast is that over the next 5 years, the traffic is going to over double. This is the mobile traffic, but it doesn't mean that any other fiber types or hard lines don't have anything to play here. As I mentioned earlier, the tower to DC connections are really viable applications for hollow core fibers. So meaning that over the next 5 years, the mobile traffic alone will be increasing. Then adding any kind of data center activities around the world, globally at the moment, this is looks like hollow core fiber is one great solution for these demands. And in general, any large scale industrialization is still in progress. So again, comparing to the telecom fiber industry, it is finely tuned to the near perfection at this moment. Hollow core fiber industry is getting there. Just not there, not quite yet, but getting there. And in summary, adding to these hollow core fibers, they are subject to patents on different fiber designs. Production may need licenses or research and coming up with own designs. And in general, manufacturing any hollow core fiber requires fiber design know-how. It requires process know-how, and it requires high precision equipment adapted to those fibers. But when mastered, hollow core fiber provides unmatched performance in a wide variety of different applications. And that's about it for me today. I thank you for your time and your attention. And in summary, here's my contact info. What I hope that you get from this is that specialty fiber and hollow core fiber and Nextrom go well together. Just remember those two things, and you can reach out to me. Also, I'll be in San Francisco in Photonics West. Feel free to drop by. Let's have a chat. Let's talk about your needs and your ideas. We'll be in booth 5404. And that's about it.
Thank you so
Thank
much,
you.
Joni, for introducing viewers to manufacturing solutions for hollow core fibers. We do have a couple minutes here for questions here. So everyone that's joining us in the audience, if you haven't already, go ahead and type your questions and comments into the chat box. Joni, beyond the examples you shared earlier, what are some potential use cases that could benefit from hollow core fiber?
Well, I do think that the medical realm hasn't really developed so much yet, so I'm pretty sure that there's going to be a lot of different new applications in there, and the sensing technology can benefit from these a lot. One place where I see that hollow core fibers might go is space. For example, radiation resistance and thermal stability in the hollow core fibers are really a benefit to use in different space applications, both in Earth, in orbit, or in different planets.
Awesome, awesome. Do you see do you see hollow core fiber replacing other fiber types at some point, or will kind of remain like a complementary technology?
Very hard to say. If only I had a crystal ball to see it for the next 10 years. The benefits of the hollow core fibers are obvious. And at this point, manufacturing the hollow core fiber is still so expensive that it will not be, I don't see it overthrowing standard telecom fibers for a moment. And I do think that there will be a ecosystem of different types of fibers that these complement each other. Hollow core fibers, standard telecom fibers, multi-core fibers. There will be a place for every one of those.
What is the loss rate of hollow core fibers at 1.55 microns?
Excellent question, and I would need to dig into my brain a bit further. Unfortunately, I don't remember it by heart at this moment.
That's very fair. That's very fair. Another question we had, do you see a path towards multi-core fibers?
Yes, there is a path towards multi-core fibers. So depending on deployment or where you need to deploy it. So multi-core fibers benefit from the space savings. So for example, in high density metro areas, multi-core fibers do have a place for deployments. So yeah.
Awesome, awesome. What aspects of hollow core fibers limit its wider adoption?
At this point, I will say that the cost to manufacture the fiber, as I mentioned earlier, there's a lot of different challenges compared to standard telecom fibers. So this is still, the price is still driving the wider adoption. But I'm sure as the manufacturing technologies evolve, the price will eventually come down, and seeing where the standardization might go, then who knows, maybe in 10 years, we will enjoy the hollow core fibers coming to home.
To kind of build on that a little bit, can you kind of speak a little bit about the major cost drivers for hollow core fibers?
Well, the cost drivers, of course, manufacturing the preform itself is much more work heavy. So there is lots more process steps, and you need to ensure the cleanliness at each step. Also, the fiber draw itself, there are it is so much more critical to keep accuracies and the pressure controls, etc. And the yield is still in a growing place. So the yield is not yet in such high rates as it is in telecom fiber, for example. So there is still a lot of learning to do.
Yoni, we have a wave of questions coming in. Do you have time for a couple more?
Sure, no problem.
What is the longest dimension you can make today? Excuse me, what is the longest dimension you can make today? And that's a follow-up to the person speaking about the loss rate at 1.55 micron.
Longest distance you can make.
Longest
Uh,
dimension they wrote.
Longest dimension, I'm assuming that we're talking about preforms. We are capable of going up to 100 millimeter diameter, and with the preform length, practically whatever you can do with telecom fibers, we can do with this equipment also.
Gotcha, got you. All right, to wrap up here, I have a five-parter here that I'm going to walk you through.
Okay.
The first one, what types of anti-resonant hollow core fibers can you manufacture?
What types? Well, this is a practically any. So as I mentioned, the preform plug itself is really critical in there, and as this is not in our portfolio, if we come up with together with a preform plug, then practically any type of fiber. Of course, remembering that if the specific fiber is proprietary to someone else, if there's a heavy amount of patents, then that's that needs to be solved before.
That makes sense. That makes sense. And I apologize if any of these are double up. Just give me a shout if so. What is the size of the cladding bare fiber diameter that can be made?
The cladding bare fiber diameter, of course, depends a lot on the customer design, but generally we can go from sub 100 micron up to millimeters. So there is a really wide range. I would suggest that take notes on the email and hit me up with a question. We can talk more about this afterwards.
That's the key with this too. Everyone in the audience, please keep track of Joni's email. And additionally, if we don't reach to your questions, please keep an eye out for a response at a later date. What is the typical numerical aperture for the fibers that you can manufacture?
Typical numerical aperture. Again, delving into customer design, so difficult to pinpoint.
That makes sense. That makes
Anything.
sense. Sorry to jump on you there. The last part of this question, and thank you for bearing through it. We're very grateful for your time. What noble gas do you use in the hollow core fibers?
What noble gas? So first of all, in drawing the fiber, we use argon, and in case you want to put something inside the fiber, this is up to customer. So we don't put anything in there, and we don't require. We haven't seen that there is no gas required during draw inside the fiber. So.
Awesome, awesome. Hey, Joni, thank you so much for taking a couple extra minutes here to answer some questions. And as a reminder, if we did not get to your question today, don't worry. We will be following up with viewers via email, so keep an eye out for that. And if you think of something later, you can always contact Joni directly at the email provided, or you can reach out to us at webinar@photonics.com. Before we go, I'd just like to thank our presenter, Joni Aaltonen, one last time. And finally, this webinar is presented by Nextrom and hosted by us at Photonics Media. Thank you all so much for joining us.